Okay, we are in section 11.9. This is representations of functions as power series. So the general concept here is that we are going to take functions which are not power series, they are not polynomials, and we're going to make them polynomials. So we're going to take something like e to the x, and we're going to write it as a polynomial. We're going to take something, like a log, and we'll write it as a polynomial, things like that, or trig functions, and we'll write them as polynomials, so that the polynomials basically fit the original function very, very well. That's kind of the idea of what we're doing here. So we're going to start off with, again, the idea that we started talking about from last time with these power series in 11.8. A power series is a series which can be written in the form of the sum of c sub n x to the n power. Now, the c sub n stands for some kind of a coefficient, but what you'll notice is the coefficients in this are c sub 0, c sub 1, c sub 2. The coefficients here are not necessarily going to always be the same number. The coefficients can actually change based upon some kind of a rule, whatever the rule is that's given to you in your sum. And then x to the n power basically just looks like some kind of a geometric, where x is being raised to an nth power. All right, so if we take a look at a few different series, you'll see what I mean about the coefficients here. And this is just kind of giving us somewhat of an idea what we're going to look at. So here in the first one, if we were to start with 0, you'll end up with 0 x to the 0 power plus. Then if you plug in 1, it'll be 1 x to the first power plus 2x squared plus 3x cubed, and so on. Okay, and hopefully you can see there again the coefficients of each one of those polynomial terms is changing, as well as obviously the power of the polynomial itself. All right, let's take a look at the second one. Again, if we start with n equals 0, we would end up with 1 over 2 squared, plugging a 0 in for n, x to the 0, plus 1 over, let's see, plug in 1, you'll end up with 2 cubed, x to the first, plus 1 over 2 to the fourth, x squared, and so on. So your coefficients here are 1 over 2 squared, 1 over 2 cubed, 1 over 2 to the fourth. And yes, of course, I know we can simplify those. I'm just showing you how the patterns are developed here. And then in the last one here, the only difference between doing this one and the other ones here is that we've got this alternating term. So if we start with 0, negative 1 to the 0 power, 1 over, let's see, that'll be 0 factorial, plugging in a 0 for n, and then x to the 0, plus negative 1 now to the first power, because I'm plugging in 1s now, 1 over 2 factorial, x squared, plus negative 1 to the second power, 1 over 4 factorial x to the fourth, and so on. So again, you can see that your powers are, your coefficients are changing, as well as the exponents. But what we've done is taken all these different things here, and we're basically writing polynomials or power series out of them. And that's what the power series is doing here. We are going to end up creating polynomials out of things which are not polynomial. All right, this section is going to end up being done in 2 videos. I'm going to get through in the first video basically how to rewrite functions as power series in one way, and then in the second video we'll actually use some calculus with that. Okay. So we're going to represent functions as sums of power series by manipulating a geometric series. Well, the idea behind this, and this is, again, where I bring everything back to the basics that we started off with way back when we started talking about series in the first place. If this is a geometric series, and that's what this is right here, it's a geometric series, it follows that pattern of a geometric series. where you have some kind of a common ratio. In this case, your common ratio is x raised to the n power. You can see that if you were just to start plugging in 1, 2, 3, 4, and so on, you would get 1 plus x squared plus x cubed. But we already know that the sum of a geometric series is a over 1 minus r. Well, a is your first term. There's a. 1 minus r, well, again, x is your common ratio here. So this is going to be convergent as long as the absolute value of x is less than 1. That was the idea for the geometric series, for a convergent series, to have a sum. So therefore, the function f of x equals 1 over 1 minus x is the sum of a power series. To write a function as a power series, we basically need to get the function into that general form, a over 1 minus r. Once we get the function into that form, we can plug a and r into the geometric series sum notation and actually come up with a sum. All right, so I hope that you will see that this is going to make sense as we go through it. I'll try and go through at least the first couple of them pretty slowly so we can see what's going on. We want to find a power series representation. So we want to find something where it is in the form of a sum for 1 over 1 plus x squared. So the biggest thing is to see, okay, can I possibly write that in the form of a over 1 minus r? Well, let's see. I have an a on top, so that seems pretty logical that a is going to be 1, since a is my numerator. Let's write that a little bit better. There we go. And if I want to rewrite 1 over 1 plus x squared so that it looks like a 1 minus r, I would have to write it as 1 minus something. Well, if I'm going to get if I'm going to get a plus x squared, it has to have been a minus x squared. So 1 minus negative x squared is going to work, which means that my r value is negative x squared. So now I have my a and my r. So I always do it this way because I think that this helps. We're going to build our function. We are going to start off with the fact that we know 1 over 1 minus x. That is given, and that's way back up at the top, that is given as the sum of x to the n power, as n goes from 0 to infinity. That is what 1 over 1 minus x is defined as a power series. Well, I want to create it so that it's 1 over 1 minus negative x squared. I want to substitute the r in for x. So now I'm going to write this as 1 over 1 minus, substitute r where the x is, negative x squared. Well, what we literally just did was we substituted negative x squared into x. So to write this as a power series, in the series itself, we are literally going to substitute negative x squared in for x. So I hope you can see that the negative x squared took the place of the x. Okay, and technically that is the power series for 1 over 1 plus x squared. Now I'm going to let you know this is not the way you're going to commonly see it written. You're going to actually end up doing a little bit of manipulation and distribution from here so that you can actually see the more common way this is done. And the reason for that is because there's going to be other things that you're going to want to do to manipulate it later. So we're going to rewrite this, because technically there was nothing wrong with it, but we're going to rewrite this. We're going to distribute the n to everything on the inside, which means we're going to distribute it to the negative sign. We're also going to distribute it to the x squared. When you distribute the n to the negative sign, keep in mind that negative sign is basically like a negative 1x squared. So this is going to become negative 1 to the n, distributing the n to the x squared, multiplying the exponents together, you get x to the 2n. Okay, this is the more common way you will see the power series representation for 1 over 1 plus x squared. All right. Again, if this isn't making sense, maybe stick with it for a couple of examples and see. And if it is making sense, then we're going to move on. If you need to go back and watch some more, go back and try, try and watch it a little bit slower, see what's happening. That's fine. There's going to be a lot of algebraic manipulation in this. So there's a lot of algebraic concepts here. All right, let's find a power series representation for 1 over x plus 2. Again, the general idea is we're trying to get it into a form that it is 1 over 1 minus x, or something like that form. So I can start by simply rewriting this as 1 over 2 plus x. I just basically shifted the x to the right in the denominator, so I have the x in the right spot. But I really need that denominator to be a 1, not a 2. Well, one of the ways you can think about doing this is I can simply multiply the top and the bottom by 1/2, or you could factor out a 2 from the denominator. There's a whole bunch of different ways to think of it. I think personally multiplying the top and the bottom by 1/2 is the easiest way to do it. So if you think about multiplying the top and the bottom by a half, this really is the same as 1/2. 1/2 of 2 is 1, and then 1/2 of x is 1/2 x. And we need it to be minus in the denominator. So we need that to be a minus 1 minus something. So we're going to write this as 1/2 over 1 minus negative 1/2 x. Okay, all of these are exactly the same. This is all exactly the same as 1 over x plus 2. We've just rewritten it in a way so that it's easy for us to be able to tell what a and r are. So a here is a half, where r is negative 1/2 x. Okay, and that's important because now we can go ahead and build our power series. I always start off with 1 over 1 minus x. That is the given one, that is the known one, that is just x to the n. N goes from 0 to infinity. Make that look a little better. N equals 0 to infinity. That still doesn't look like a 0. Better. There we go. Okay, so the first thing you do once you've started this is you look to substitute your r. So substitute the value for r. So now it's 1 over 1 minus. I am going to plug in negative 1/2 x where the x was. Negative 1/2 x, which means on this right side of the equation, I am also going to substitute negative 1/2 x. So it'll be negative 1/2 x, all raised to the nth power. Again, because we're going to do a little bit more with this one, I'm going to simplify it a little bit. I'm going to go ahead and distribute the n to everything. I'm going to distribute it to the negative sign because there's going to be an alternating term. I'm going to distribute it to the 1/2, and I'm going to distribute it to the x. So let's see, that's going to be the same thing as the sum of negative 1 to the n. So I'm going to distribute it. The one part on top is 1 to the n, which is 1. The 2 part on the bottom is going to be 2 to the n. So it's really going to have a 2 to the n in the denominator, and then distributing to the x is going to give me an x to the n in the numerator. You could have made it 1/2 to the n, but it's exactly the same thing. Okay, so now I'm down to what would hopefully be our last step. Now I have to introduce the a value, but the a value is not substituting anything. It's literally multiplying the top of the fraction by a. So we are literally going to multiply the numerator by 1/2. I'm going to rewrite my denominator now so that it looks like 1 plus 1/2 x. And now I am going to not substitute, but multiply my current sum by 1/2. You could technically put the 1/2 out in the front because it is a constant, although a lot of times we're going to distribute it because the multiplying this thing right here by 1/2 is really going to be multiplying, I'm going to erase this in a second here, multiplying that by 1/2. You can see that the bottom, the denominator, has a common base of a 2. So when I do that, I'm going to actually be able to change the exponent. So the negative 1 to the n won't change. X to the n on top won't change. But the 2 multiplied in the denominator, because again it's multiplied by half, is going to be 2. Now 2 to the n times 2 is going to be 2 to the n plus 1 power. This is a power series representation for 1 over x plus 2. And I realize that that looks like a 4. That's supposed to be a negative 1. There we go. So again, rewrite the original function so that it looks like it could be put into a 1 over 1 minus r, or a over 1 minus r form. Figure out your a, figure out your r. Start with the original function 1 over 1 minus x, substitute in your r, simplify a little bit, and then multiply everything by a. Okay, let's try another one. Well, the good news is, if you're paying attention, this looks very similar to what we just did. The only difference here is the numerator is now x cubed, where up here it was just 1. Otherwise, it's still over x minus 2. So I can kind of use what we just did to get this one without doing a lot of extra work. I already have 1 over x plus 2. We did that up in the top. That's what this is. So that's going to be the sum from n equals 0 to infinity of negative 1 to the n, x to the n, over 2 to the n plus 1. That is 1 over x plus 2. What you should notice here is the only thing I've done to this function now is I've multiplied the numerator by x cubed. Otherwise, it's the same thing. So I'm going to multiply by x cubed on both sides of my equation. Which means, again, this negative 1 to the n doesn't change. That doesn't have anything to do with x. But the numerator has an x to the n power, so when I multiply x to the n times x cubed, that is going to give me x to the n plus 3 power over 2n plus 1. And that's the power series representation for x cubed over x plus 2. That one would have been a little bit harder just to start with if we hadn't already done something up front to get to a certain point. But it could still be done. All right, a couple more on this video. Let's check our time. Okay, we're at 17 and a half. A couple more on this video right here, and then we will stop it and we'll come back with the second video. All right, so this one right here, 4 over x plus 2. Again, this is very similar to what we just did. We already had the 1 over x plus 2. Okay, and that was our sum. N goes from 0 to infinity. It was negative 1 to the n, x to the n over 2 to the n plus 1. And so you might be thinking, well, why are we putting this one on there? We've already done things just like this, and we could just multiply it by 4. And you're right, we can just multiply it by 4. The reason I want to do this one is because while you could literally just multiply this thing by 4, and you could put a 4 up here, which I'm going to erase, and that would be correct. It just may not be the way that you see it. And the reason for that is because 4 can be written as a base of 2. So it's going to alter that denominator a little bit. So 4 as a base of 2 is 2 squared. But I could also write that as 1 over 2 to the negative 2. Hopefully that makes sense. 2 to the negative 2 power. 2 squared is 4 in the denominator, but if it's to the negative power, you'd bring it up to the top. So these are all three exactly the same things. So the reason that that's important is because this is the same thing as 4. So when I multiply that by 4 here, it's really going to be introducing that 1 over 2 to the negative 2. So again, this part doesn't change, the x doesn't change. But if I multiply 2 to the negative 2 times that denominator, 2 to the n plus 1, adding the exponents, I now get 2 to the n minus 1 power. And that's it. That was the main reason I wanted to show that particular problem. Because you might have a 4 on top and be like, why is that any different? It's algebraically the same, but I just wanted to make sure that you could see that. All right, one more. And then, like I said, we will go ahead and stop this video and come back with a second one. Okay, so we need to put this in the correct form. First of all, we want that 1 on the denominator out front. So we really want 1 minus x squared. But I can't just arbitrarily change the signs. But what we can do is multiply the top and the bottom by a negative value, which means you'll also change the top sign. So we'll flip the top as well. Okay, so really what I just did there was I just multiplied the top and the bottom by -1, and then that alters the sign so we can change the order. Okay, at least the denominator now is in the 1 minus form. So it's actually pretty easy from here. A is your numerator, 1 minus 3x, where r, well, it's already in 1 minus, so r is just x squared. So let's write the function. 1 over 1 minus x, that is your baseline. That's where we start. And that's going to be x to the n power. Substitute in the r. So I am literally going to plug in x squared where I had x. So now this becomes x squared to the n power, which, rewriting it, there's no negative sign to worry about here, so I literally just distribute the n to the x squared, and we get x to the 2n. Then the only other thing we have to do is multiply it by our numerator, which is 1 minus 3x. So we'll have a 1 minus 3x on top. And now we have to multiply this thing by 1 minus 3x. And again, that technically is your sum. It just isn't going to usually be left like that. So we'll distribute the x to the 2n. So we're going to get the sum of x to the 2n minus, let's see, multiplying 3x times x to the 2n will be x to the 2n plus 1. And I'm sure you heard that telephone go off. The joys of recording these from home. I guess I could have been at school and had some random announcement come on right in the middle of the video, which has definitely happened before. Anyway, that is it for that one. So that one right there is the representation for 3x minus 1 over x squared minus 1. We'll come back with a second video in which we're going to do a little bit of actual calculus with this stuff.